Okay. Welcome, everybody. Thanks for coming in. So we have two talks today. First talk is going to be remote and second in person. Let me introduce your first speaker is Stephen Bromley from Auburn University. Stephen graduated with his PhD in atomic physics in Clemson University in 2020, and then from 2020 to 2023, he undertook a postdoc position at Auburn University, where he worked on producing atomic data and developing spectral models for both laboratory and astrophysical plasmas. And since 2023, he's taken the role of principal research scientist at Auburn, where he works on providing atomic data through computational and experimental means for spectral models of transient events, and in particular Kilonovae. And today is going to talk us about atomic data needs for non-equilibrium modeling of Kilonovae. Stephen, the floor is yours. Thanks for joining us.
Thank you for having me. Uh, so, what I wanted to talk about today is maybe a bit exotic for some of the audience, but I think is a really interesting topic. So, these kilonovae are the sort of electromagnetic transients that result from a neutron star merger. And while they're quite astrophysically interesting, under the hood, they are sort of an atomic physics playground. And so, what I'd like to do is give sort of a big picture overview of the atomic physics side of these events and sort of the atomic physics you might need to consider as they evolve in time. Early on, it's a very radiation-driven environment. There's a lot of complex radiative transfer, and then as time goes on, the radiative transfer simplifies, but we get very exotic and unique atomic physics, in particular with multiple populations of electrons. And then at the end of the talk, I'd like to talk a little bit about some of the projects we're doing to provide atomic data for these non-equilibrium models and where we're going. And so just to start, I wanted to give sort of a big picture overview of kilonovae and their time evolution. They evolved similarly to a supernovae, although on different timescales. And so what I'm showing here is a nice graphical description of the time evolution of a kilonovae or explosive transients in general. This is from a review article from Anders Björkstrand back in 2025. If you're interested, it is a rather excellent review paper. Um, but you can think of this in sort of two ways. The first is early on we have some explosive event. The ejecta is very optically thick, it's very dense, and so the spectra we're seeing is primarily from the outermost layers of the material. As time goes on, as this remnant expands and diffuses, eventually we hit a sort of tail phase. Some might call this a nebular phase in the literature. And in those, the radiative transfer simplifies, but we have many more atomic collision processes that we need to consider. And of course, as time goes on, we become more optically thin and we start to see deeper into the ejecta. And so on the right here, I'm showing just a comparison from Björkstrand et al. Some of the properties of kilonovae. In particular, the average composition is much higher in Z compared to a supernova. The expansion velocity is very different. In a supernova, it might be a few thousand kilometers a second, but in kilonovae, it's a rather substantial fraction of the speed of light. This also has a couple consequences. The first is the diffusion timescale for supernovae is much larger than a kilonova. So comparable evolution in a supernova you might see in a year. In a kilonova might happen on, say, week timescales. There's another complication here in that while both kilonovae and supernovae are powered in some part by radioactivity, in kilonovae most of the ejecta is radioactive. And this is going to couple into the atomic physics I'll talk about here in a minute or two. And just to give a flavor, I'm showing here a couple different sources of heating in kilonovae. This is from Winajo et al. In 2019. On the left, we have heating from beta decay. We recall the ejecta is radioactive, and as these things beta decay, a neutron turns into a proton, and our composition increases in Z. That also has a consequence that this is delivering heating into the plasma. We also have heating from alpha decay and fission, and all three of these thermalize with the local plasma at different rates. I also wanted to make a note that a lot of this nuclear data is quite uncertain. It's sensitive to things like isotope masses, beta decay rates, and in some cases those can be measured. in various beam facilities. Uh, but for some of these more exotic isotopes, it's very difficult or impossible to measure, and so we're mostly relying on theory. And so just to dig into the atomic physics a little bit more, what I'm showing here is a time series of the spectra from AT 2017 GFO. This was the kilonova that followed the first binary neutron star merger gravitational wave detection back, I guess, almost a decade now. And this time series is from Sneppen et al. We start here at the top at about a half day after the merger, and then all the way at the bottom we have spectra at 10 days. And it has a rather interesting evolution. Early on, it looks like a black body that peaks in the ultraviolet, and then as time goes on, this black body cools off. The peak of the emission shifts more into the visible and the infrared. And we also see a couple interesting spectral features pop up. You can see one here around 1.1 micron or so, and I have some cutouts on the right from Stempen et al. And this very interesting line shape, a P Cygni feature, arises mainly from the velocity structure of this ejecta. If you recall, the ejecta is expanding at a significant fraction of the speed of light, but the ejecta is also fairly stratified, so the outer layers are moving much quicker than the inner layers, and so we end up with this velocity gradient as we move outward, and that gives rise to these nice P Cygni features. And so, if I was an astronomer and I wanted to model these, you would probably adopt an expansion opacity formalism. And at this stage, now we start to dig a little bit more into the atomic physics involved. And thankfully, early on, the ejecta is quite dense. And so there's a couple assumptions we can make to really make our lives as modelers easier. And so at very high densities, we could assume that the plasma is described by Saha equilibrium. So our ion fractions here, n, are given by a Boltzmann factor containing our ionization potential and a characteristic temperature. We can also assume that things are dense enough that the level populations within each ion are in some sort of equilibrium, here in LTE. And in that case, our level populations given by m are again proportional to a Boltzmann factor containing that energy and a characteristic temperature. So what we would need to know really to build a model based on these expansion opacities would be to run off electronic structures for all the ions of interest, compute a Saha equilibrium, compute the level populations in LTE, and from there we can develop our opacities. And so very briefly, for every single transition described by a wavelength and a transition rate, we can compute an optical depth, and then we can sum these into an expansion opacity. And I want to make a note here in that this approach lets us simplify the modeling quite a bit. And what I mean by that is you could run off a very large electronic structure, make it as accurate and as complete as you can, and then you can tabulate these opacities. And this has been done for well over a decade now by various groups in Japan, Sweden, all across the US, Los Alamos, and many more. And there's a little bit of a problem here, in that this expansion opacity formalism works great for describing the radiative transfer in the very early stages of the kilonovae, but about a week after the merger, the models start to disagree with the observations. And this is mainly because our two assumptions here, the Saha equilibrium and this thermodynamic equilibrium, start to break down. So instead of having a nice simple ionization and excitation structure, now we need to start to consider some of the microphysics. And just to build up a sort of mental picture of what's going on, as a function of time, our density is decreasing because this ejecta is expanding out quite rapidly. Our radiation field is being diluted, and our temperature is also evolving quite interestingly in time. So the temperature is still a bit of an open question. We know the black body is cooling off as a function of time, um, but there's also heating continually going into this ejecta, and also the cooling is going to depend on things like how efficiently some of these infrared lines that are optically thin are excited. And so the temperature is very much still an open question. Um, some of the early things that were looked at in these non-LTE models, just as an example, there was a thought at a time, you know, if things are still not dense enough for LTE, could this radiation field that's still around sort of prop up the level populations or push them to an almost equilibrium state? This was addressed in some of the early non-LT models by Pognan et al. And Anders Björkstrand's group. And the short answer is that they can't quite prop up the populations, but they still contribute. You know, they still excite levels, they still ionize. So we can't quite ignore the radiation field, but its importance is sort of decreasing over time. And so If we can't make that simplified approach, we need to start to consider all the ways that these ions could be excited or ionized in this plasma. And so I'm showing here just a graphical description of some arbitrary ion I'll call A plus. And there's a couple different ways we could excite the levels here in these ions. They could absorb a photon from the radiation field. They could be excited by either thermal or non-thermal electrons, and I'll talk about those populations in a moment. Um, we also have to consider how these ion stages are coupled together. Neighboring ions can be formed by recombination from higher ion stages, but ions can also be formed from ionization, either from the radiation field from UV photons or from ionization by these non-thermal electrons. And so all of these processes are described by, in some cases, a cross-section, in others, a rate coefficient. And the ones that really matter are going to depend on these two electron populations. And so I mentioned thermal and non-thermal electrons, and I just wanted to talk about them briefly. Our thermal electrons are relatively cold. We think these are on the order of a few thousand Kelvin, say a fraction of an eV. Typical densities, just to give you a ballpark estimate, on the order of 10 to the 6 per cubic centimeter. So quite thin, but compared to the non-thermals is actually quite large. And because these are relatively low temperature, they combine quite efficiently with ions, and I'll talk about DR in a little bit here. But the non-thermal electrons, I think, are where things get very interesting. These are produced at very high energies on the order of hundreds of keV to MeV. These are the result of beta decays in this very radioactive ejecta. And while their densities are very low, on the order of 10 to the minus 2 per cubic centimeter, so we have about an 8 order of magnitude difference between these two populations, these non-thermal electrons deposit a lot of their energy through exciting the plasma, through ionizing things, and through heating the thermal electron population. I won't go into it in any detail, but I'll just mention that the evolution of these non-thermal electrons can be described by the Spencer-Fano equation. And I just want to make a note that the degradation of these non-thermal electrons really depends on cross sections. If we were to look out in databases that store, sort of collisional data sets, what we'd often find are thermally averaged rate coefficients. So somebody has taken a cross section and then averaged it with a Maxwellian at some temperature, and that gives you a thermal rate coefficient. Unfortunately, the energy distribution of these non-thermal electrons is very, very far from a Maxwellian, and so that form of atomic data isn't really applicable. And so there's a bit of a disconnect here between the sorts of data that people would usually publish or usually distribute and what is really needed to describe the electrons in this environment. And so with that, all these collision processes, whether it's recombination or ionization by these non-thermal electrons, we need atomic data describing these processes. And in general, the cross sections that one would need don't really exist. And so, in the absence of data, the best you can do, at least as a start, will be to utilize some of these empirical expressions that have been around for, in some cases, a few decades now, just to get a ballpark estimate of what some of these cross sections might be. And for electron impact excitation, this is things like the work of Van Regemorter back in the 60s. For ionization, we have the rather famous ionization cross sections from LOTS, which, as I'll show in a few slides, actually does pretty well fairly often. For photoionization, the best we have at the moment are hydrogenic cross sections. And for recombination, there's not really a good approximation for a DR rate. Um, there's some out there, but they tend to be very, very off depending on the use case. And so at the moment, there's just order of magnitude estimates. And so most of the projects we do at Auburn, I mentioned at the start of the talk that I'm not an astronomer, I'm an atomic physicist. And most of what we do is try to provide these cross sections to the non-LTE community. So using things like autostructure or the flexible atomic code to produce cross sections. And then once we have them, we try to understand, what is the impact of updating these atomic data. If we were to report an ionization cross section that differed by a factor of 2 from some of these approximations, how does it affect the ionization balance? Is it the 5% level, 10%, order of magnitude? And so what we try to do is build, simple test models to try to probe the impact of this updated atomic data. And so with the last few slides I have, I just want to comment on a couple of our ongoing projects to update some of these atomic data. I'll highlight some of the level of improvement that can be made, and then at the end we'll kind of summarize what is needed and make note of where experimental measurements might be really helpful for this field. And so I'm going to go through three of these processes here: electron impact excitation, ionization, and recombination. I am interested in photoionization, but at the moment we don't have anything ongoing in that arena. And so for electron impact excitation, I'm showing here the approximations that are currently in use. For dipole allowed transitions, this is the approximation of Van Regemorter, and for Axelrod, this is for forbidden transitions. And what's convenient about these is, say you had an electronic structure that you ran off to compute opacities, you would have wavelengths, you would have Einstein A coefficients, and so you could generate this collision data quite easily. And just some jargon here, I'm actually showing this psi is an effective collision strength. You can think of this as just a thermally averaged cross section. It's a dimensionless value. And a couple years ago, we were working on some data for platinum, and we had an idea to generate R matrix and distorted wave electron impact data for platinum ions, and then just to gauge how accurate these empirical expressions are, just compare our resulting rates with the Van Regemorter data. And so what I'm showing here is a comparison for platinum 1, 2, and 3, the effective collision strength for every single transition using this approximate data divided by its value in the what we think is very accurate R matrix approach. And each dot here is an individual transition, and there's two things you can notice. One, there's a very large scatter on whether or not the Van Regemorter approximation is accurate. And the second you'll notice is that even with that scatter, there's a rather large systematic underestimate of this effective collision strength. And what this might mean in a kilonova model, if our cooling is determined by exciting transitions and decay in the infrared, if we're underestimating the amount that those transitions are being excited, we might be dramatically underestimating the cooling, and so there's some impact on the temperature evolution in a kilonova. And I'll also mention it's sort of one thing to calculate this sort of collision data. You could ask five different people to compute the same cross section, and you might get five different answers. And so it can be very helpful to have a sense from experiment of how accurate your collision data is. And so what I'm showing here is there's a lot going on here, but I'll walk through it piece by piece. I'm showing an overview figure of an experimental campaign we're building here at Auburn to benchmark some of this collision data we're producing for Kilonovae. So the first thing we would do is look in these hollow cathode lamps. These are small benchtop experiments that erode and excite an element of interest inside a neon buffer gas. We then work out where that ion is emitting, and once we know where it's emitting, then we go on to a larger experiment here in our department called the compact toroidal hybrid. This is a cross-section view of this device. This is a hybrid stellarator or tokamak device. And the idea is quite simple. We take the element we want to study, we stick it in on this probe here into the machine, we fire it off at a variable set of plasma conditions, and we collect a spectrum. What we then try to do is generate a synthetic spectrum using our electron impact data and compare these two. And once we've nailed down the modeling side, we can then compare the electron temperature and density we need to match that spectrum with the actual conditions we can measure locally with a Langmuir probe. And so very recently, we've tested this new Langmuir probe with a nickel target inside this device, and we're now moving on to a campaign on disk-shaped targets. As it turns out, machining some of these very high Z elements is quite difficult, and in some cases is not very safe. For example, zirconium, when machined, has a habit of catching on fire, and so there's some safety complications there. But we're planning a campaign with disk-shaped targets in the near future for a couple of these elements, zirconium, tellurium, and neodymium, that are very much of interest to these spectral models. Moving on to these other two processes, ionization and recombination. At the moment, we have a campaign going on to compute ionization and recombination data for a couple different elements. There's, of course, a great many ions that are of interest to this R process nucleosynthesis. But at the moment, we've selected three of these for study: strontium within the first R process peak, tellurium within the second, and then osmium within the third. Each of these has sort of a representative electronic structure of most of the elements in that peak. So, for example, strontium has a valence S shell, tellurium has a valence P shell, and osmium has a valence D shell. And what we're doing is just computing ionization rate coefficients, ionization cross sections, DR rate coefficients, that sort of thing. And just to give a flavor of the level of improvement that can be achieved, I'm showing here dielectronic recombination rate coefficients as a function of temperature for a couple different tellurium ions. That's our data here in blue. And what I'm showing in red is our order of magnitude estimate that is often used in some of these kilonova models when data doesn't exist. And so in some cases around, a few thousand Kelvin, like in the case here for tellurium 3, it's actually fairly close to this empirical value, but in other cases we can be off by factors of few or even an order of magnitude. And this can have a very large impact on an ionization balance. I also wanted to note that experimental measurements would be extremely valuable for troubleshooting these, um, or rather diagnosing how accurate these calculations can be. Calculating rate coefficients at low temperatures is extremely difficult because the electronic structure is very difficult to calculate for those near threshold resonances. Unfortunately, the large charge to mass ratio for a lot of these R process elements is a bit prohibitive for doing something like a storage ring measurement. Moving on to the last topic here, our ionization. I'm showing here two examples. This is data we've computed for ionization of singly ionized tellurium, and on the right is ionization of singly ionized strontium. On the left here, all of the solid lines are our calculations, and then the empirical lots formula is here in green. And so in the case of tellurium, we actually match the cross-section reasonably well around the threshold, and then if we go all the way out to high energies, where it might matter for non-thermal electrons, it's actually pretty close to our explicit calculations. On the right here, I'm showing the ionization of singly ionized strontium, and this is actually a case where the lots approximation does quite poorly. So very low energies, we have mostly direct ionization, where lots does reasonably well, but at a certain point, we have intershell excitation here, which gives rise to this huge excitation autoionization contribution, and in that case, the lots approximation is off by quite a bit. Just to give a flavor of why you might care about these cross sections, I can show a couple ionization balances using our updated data. So on the left here, this is a typical ionization balance in Saha equilibrium, and then in the dashed lines are a non-LTE ionization balance with just the thermal electrons. If we add in the non-thermal electrons described by our updated cross sections, we see that not only do we get a lot of ions at lower temperatures, but there's a very large scatter here depending on the empirical cross sections. Um, and so in some cases where the LOTS cross section does reasonably well, in others it does quite poorly, and in both cases of DR and ionization, it can have very large impacts on the ionization balance in these kilonovae. And so I'm just about out of time, so we can go ahead and wrap things up here. I just wanted to summarize that, in the first, say, week or so of a kilonovae, on the atomic physics side, this is really an electronic structure problem. We need to know energy levels, radiative rates, opacities, that sort of thing. And around that week point, around a week after the merger, our non-equilibrium models really kick in. And in that case, you need cross sections for ionization, you need rate coefficients for recombination. And so it really starts to become a sort of atomic physics playground. And just to reiterate from my title slide, what I really think here is the atomic physics understanding of these events is really at the heart of enabling abundance diagnostics of kilonovae, really getting at what elements are being produced and in what quantities. And so with that, I just wanted to mention that our recent work on tellurium is now up on arXiv. I've put the abstract here. Of course, if you have any questions, feel free to email me or get in touch. I'd be happy to chat. And I'd like to thank everybody for your time, and I'm happy to take any questions.
Thank you, Steve. Okay, so let's start with our question session. Do we have questions?
Hello. The DR rate can be pretty sensitive to density when you get to densities like 10 to the 10, but not at densities like 10 to the 6 typically. What density range are you looking at, and are you trying to compute the density sensitivity?
That's a good question. So I think early on, when the densities are around that 10 to the 10 point would be, I think, very early on in the first couple days where things are pretty close to equilibrium. Once we hit this nebular phase at about the 5 to 10 day time scale, I think a typical density is on the order of, say, 10 to the 6, 10 to the 8. And at that point, the density isn't so much of an issue, but the temperature becomes the issue. A lot of these low temperature DR rates, you could run most of the time people are using autostructure. You could have five different people calculate DR rates with autostructure and get five different values. And then the question becomes, which one is not correct necessarily, but most correct because these near threshold levels are extremely difficult to calculate. In a lot of cases, we're talking, levels that are within, a fraction of an EV of the ionization potential. And so, in a sense, it's still an electronic structure problem at that point. Just a very difficult one.
Thank you. Any more questions? I wanted to ask you if you plan to have a diagnostic for the non-thermal electrons.
So, could you repeat that?
If you plan to have a diagnostic for the non-thermal electrons in the lab. So you showed some plots, but these were only simulations, I think, right? Modeling.
Yeah, I ran out of time to talk about it, but at the moment we don't have any experiments to test ionization cross sections. For a lot of the stuff we've done so far, there are some measurements available from beam experiments for things like strontium, tellurium, and a couple other elements. It would be really handy if we could measure ionization cross sections, but nowadays there's only a handful of groups that are capable of doing that. I think there's a group in Germany that has built a recent beam experiment. I think the last thing they reported was, um, I think it was lanthanum ions. So for that non-thermal work, what we really need are excitation cross sections and ionization cross sections. We can do the ionization cross section measurements here in a sense, but the ionization cross sections at the moment will be relying on other groups.
I see. Okay.
Mm.
All right. Any more questions? I don't see any online. Okay. So let's next speak and start Stephen again.
Thank you. And I can stop my screen share here so our next speaker can
Thank you.
bring it up.
Let me introduce our second speaker today, Mackenna Wood. She's director of the Saunders Planetarium at Museum of Science and Innovation in Tampa, Florida. She studies young stars and exoplanet system with multi-wavelength observations, focusing on age measurements. She completed her PhD in the Young World Lab at the University of North Carolina in Chapel Hill with Dr. Andrew Mann. Following that, she completed a postdoc at the Calvin Institute at MIT, working with Moritz Goethe, known to many of us, I think, on X-ray observations of young active stars. And these days, she also manages the Saunders Planetarium, ensuring to be content and developing astronomy program while she's able to continue her research. Thanks for doing that. And today she's going to present the Oriona activity at young boards. Thank you, ma'am. Thank you.
Okay, can everyone hear me? Okay. Hi, thanks for having me. You just did a great job introducing me, so I'm not going to repeat all of this. But I do study mostly young stars and young exoplanet systems in multi-wavelength observations. And when I say multi-wavelength, I mean that I did all of my undergrad and graduate research in optical, and then did a little bit of X-ray, starting with my postdocs and onward. But so today I would like to talk about how changing stellar activity affects young evolving exoplanet systems. So we know that activity is incredibly important for shaping the final stages of an exoplanet's characteristics, right? It shapes what the atmosphere is made of, it shapes what the atmosphere looks like, how much atmosphere there is. So we know that activity is very important for shaping a lot of these things. But what is really important is how exactly that happens. And that is something that is fairly difficult to study because it only happens during those first few million years that a star system exists. And so we want to take a look at that. But before we can understand how stellar activity affects exoplanets, first we have to understand stellar activity itself in young stars. So we're going to take a look at how stellar activity changes in young stars. And we know that stellar activity changes over many different time scales. On the short end, we can look at a star over, a single observation from minutes to hours long, and we can see it change in real time. We can see flares, we can see accretion rates changing, we can see all sorts of things happening over just these single short observations. Over days or weeks with multi-night observations, we can also see changes in spot patterns and some slightly longer term changes in stellar activity there. And on the long end, over millions and billions of years, which we can observe by comparing between different young stellar associations at different ages, we can see a general steady decrease in all kinds of stellar activity, which we expect as these stars are spinning down. They're slowing down their rotation, and so their magnetic activity is going to be weaker. But the middle section is sort of more of a question mark. Observing stars, particularly in multi-wavelength observations over years and decades, is something that we're sort of just getting to the decades mark there. We're just being able to have looked at stars for 20 years in X-ray. And so we're starting to see patterns there. Activity cycles like the one on our sun have been detected in a number of other stars, but there are still a lot of question marks because we are really just getting to that point where we can look at decades of data in multi-wavelengths. And in that other column, the thousands to hundred thousands of years, I don't know of any way to look at stars over that time frame. That's longer than modern astronomy, and it's also much shorter than the precision of our age measurements. So that column is mostly question marks. But we can do a lot. We can observe a lot of things. And in particular, I am going to talk today about a set of observations on two very young stars, which hits 4 of these 5 age categories. So this is a paper on examining 20 years of observations on SU Auriga and AB Auriga. The paper is published. It's there at that link. And for an overview of the observations, we have both optical and X-ray data from XMM, Chandra, FAST, TRACE, ERAS, a bunch of optical surveys spanning over 20 years. This includes some sets of both simultaneous and optical X-ray. So you can see this, this top plot is the long plot. So no, I don't. Thanks. Okay. We've got data from the 1990s up through 2012 in the long term, and then looking specifically at the 2012 data, we have data from XMM Newton and then 3 different optical telescopes which span a couple of weeks and include a few simultaneous observations. And because both SU Auriga and AB Auriga are very close together on the sky, all of these observations include both of those stars. We can fit them in the same field of view for all of our telescopes. So to give a little more detail on those X-ray observations, since I know that is what everyone here is interested in, we hit it with XMM Newton twice. We used archival data from 2002, and then the new data from 2012, which Moritz requested and applied for in 2012 and then didn't get around to doing until now. It happens. So we've got the sort of new data from 2012 and archival data from 2002. This is total a little over 230 kiloseconds of observation on these 2 stars. Both observations include the epoch Moss and the RGS. Only the second one includes the PN data. We also have archival data from Chandra from the AGTG, which is just under 100 kiloseconds of data. So to look at these different time scales of data on the star, we can look at the minutes to hours. So these are our individual observations. The XMM Newton observations are the ones here, 2002 on the top and 2012 on the bottom, and this is Chandra over here. And here we can observe a whole bunch of flares ranging from about 1.5 to about 5 times the quiescent flux in height. These flares have lengths between about 15 and 35 kiloseconds, meaning that in total, this star, and this is SU Auriga, was in a flare state for almost a quarter of the total period of time that we were observing it for. So there's a lot of changes on these sort of minute timescales. AB Auriga, which is just a little bit more massive than SU Auriga. It is 0.2 solar masses more massive, but that puts it in an entirely different evolutionary stage, even though they're both the same age. And that one is much, much quieter. You can see these are our XMM Newton observations. The Chandra didn't really have enough counts to worry about. And it's more or less steady over the period. There is a slight sinusoidal variation in that 2002 data. It has a period of about 42 hours. But there's not any evidence for that variation continuing in the later 2012 data. So here we see less variability over this minutes to hours timescale, but still a little bit. Looking at the days to weeks timescale, this is optical data looking specifically at the H alpha line, which is a strong indicator of accretion onto stars. So here we're looking at the changing accretion onto SU Auriga over the span of about 10 days or so. And we can see the shape of the H alpha line changing significantly. So it starts out down here. This is both flux and time. So the beginning is down here and the end is up here. So it starts out a pretty large peak with a slight dip in the middle. By the middle, it is fully self-absorbed in the center, going down even below the continuum, and then it starts to increase again at the end. And so what this indicates is that the amount of accretion is changing and varying over days. We knew that back in the 1990s. This has been seen before on this particular star. But here we see that period of decreasing over about 7 days and then beginning to increase again. A little bit more clearly. This is also simultaneous with the XMM Newton observations. That blue strip in the middle are the covers the observations that were taken during the XMM Newton observation. And so we can see from the H alpha emission that there is accretion occurring during that observation, although we can't actually see it in the XMM Newton data, which suggests that the soft X-rays from that are being absorbed by something. They are there, but we can't see them in the XMM Newton data because something is blocking them. Over years to decades, we can also see much steadier flux across these stars. So here we've got a mix of archival observations of SU and AB Auriga from the 1990s through 2012. And while we saw a bunch of variation, particularly in SU Auriga on these smaller timescales, this evidence suggests that most of these stars are fairly steady over years. So we found stable luminosity across this whole 20-year period and stable temperatures over the 10-year period covered by the X-ray observations. Similarly, recent studies have found sort of basically the same thing. Herzeg et al. 2023 found stable accretion in TW Haya over 25 years, although they did see changes in the short term during that same period. And Silverberg et al. 2023 found the same thing in XZ tau, a stable coronal emission over 20 years that the data covered. So now that we are being able to see these stars over this longer period of time, it's looking like while they vary a lot on the short term, over this sort of years to decades term, there's a lot less variation. Things are a lot more stable. Again, for the thousands to hundred thousands of years, I don't know of any way that this can be done. It is too precise for our age measurements and too long for our observations. But for the million year to billions of year range, we can also look at how SU and AB Auriga will likely change over that period. The reason we can do this is because they are both part of the same young stellar association, Taurus Auriga, which is about 5 million years old. So we've got all the stars in Taurus Auriga about 5 million years old, and we can get information on other stellar associations that are older and compare to those stars to try and see how this happens over these millions and billions of years. And so that's exactly what this plot is doing. It's from Davenport et al. 2019. They looked at stars in a bunch of different associations over different ages and saw a reduction in flaring fraction over that period of time, although that is color dependent. That's what the different colors here are. So M dwarfs, very low mass stars, are up here at the top. They flare for a lot longer, and higher mass stars are here. So we can see, compare as well as the short term, we can also compare these very very long-term changes. And here we do see a pretty steady decline in all kinds of stellar activity. However, getting the really detailed information here does require accurate and precise age measurements. I'm not going to talk very much about that during this talk, but that is what I spend much of my time doing, getting those age measurements of young stellar associations so we can figure out where on the x-axis of this plot they belong. So that is an overview of how our stellar activity can change over time in stars. But now we want to go back to our question and figure out how this changing stellar activity is going to affect young planets. We know that it does. The primary driver of early photoevaporative mass loss is thought to be chromospheric emission, which reduces by 3 orders of magnitude over the first few billion years of a star's life. And flares, while most research right now finds that they're not intense or sustained enough to cause significant mass loss, they may cause significant composition changes in the atmosphere of stars. So we know that stellar activity has a huge effect on planetary evolution. And this is where we're going to take a look at a young planet host called HD 109833, which was recently observed with Chandra. So this star is a G-type member of a 27-million-year-old association with 2 super-Earth planets found around it. The 2 planets have orbits of 9 and about 14 days, and they're both a little over 2.5 to 3 Earth radii in size. Now, that is actually very small for their age. So this plot here shows a map of stars of planets of young ages. So the dots are young planets. The background contour are the general field population of planets. So we know when we find planets that there is this gap here in between the orbits of about Neptune and Jupiter. We don't generally find planets in that size. And that's again thought to be due to that chromospheric photoevaporative mass loss. It pushes everything that was here down to here. So the only things that we find in that gap are generally very young planets. And when we find very young planets, things that are less than about 100 million years old, they are usually up here in this gap. But these 2 planets that are only 27 million years old are way down here. They are much smaller than anything else their size. And so the question is, why are these planets so small for their age? There wasn't a great X-ray observation of the host star here, so we proposed for some time on Chandra to do it, and we got it. We got 10 kiloseconds of observation on the star using Chandra ACES S, and we got 12 whole counts. Which is enough to measure the flux with a lot more precision than any previous measurement had gotten. And so doing so, we found that HD 109833 is much fainter in X-ray than other planet hosts, even those with significantly larger planets. So we measured the X-ray luminosity and estimated the overall XUV flux, finding the flux incident on the planets to be about 1.3 times 10 to the 4th ergs per centimeter squared for planet B, and then a little bit lower than that at 6.1 for times 10 to the 3rd for planet C, which is a little bit further out. That is fairly high compared to most planets that we look at, but when we compare it to other young planets, we see that it's actually very, very low. So this plot here shows the X-ray flux irradiant on young planets for every planet less than 100 million years that I could find an X-ray measurement for. There aren't all that many of them. And this is the lowest flux of any of them. Most of them are much larger than these. So we've got radius on this. Radius here, so most of these young planets are, again, larger than ours, and most of them also have much higher flux levels than these, even the ones that are older than these, so that photoevaporative mass loss has had more time to affect the planets. So this suggests that maybe it isn't photoevaporative mass loss, or that there is some other mechanism involved in making these planets as small as they are, because if it was just the XUV flux, we would expect a planet that is older and has significantly higher flux to have smaller planets as well. So obviously there are many, many questions here, but this is one way of looking at how this X-ray activity affects these planets. planets. I'm going to use the last couple minutes of my talk to talk a little bit about what 90% of my time is spent doing, which is sharing the universe at the Saunders Planetarium. So I work at the Museum of Science and Innovation in Tampa, where I'm the director of the Saunders Planetarium. MOSI is a public science museum, and so a center for STEAM education for the whole area around. And we are also the second largest planetarium in the country. So our Saunders Planetarium, which is inside that giant dome building there, opened on April 1st of last year. So we've been open. That says 2026. It was last year. We've been open for just over a year now. And in that time, we've had over 120,000 people come through our regular daily shows. So that is not counting any of our special events or evening events or anything like that. So these are people who are coming through just to see the planetarium, to see the science that we do in there. A lot of that is students. We have on a regular basis 200 to 400 students pretty much every weekday throughout the school year. This is a picture of the inside of the planetarium. Gives you an idea of just about how big it is. That picture up there is of our opening. We had astronaut Nicole Stott come by, which was very cool. She's been a great supporter of the planetarium. And so we do a lot of programs in here. We do a lot of school programs like this. These are all school children that came by, but we also do a lot of other science programs. We're starting a series called Science at the Saunders that I'm trying to get going, which is to bring in active researchers to talk about their science to a general audience here in the dome. And we could do some really cool visuals with that as well. But we also do stuff that ties into current events. So this is a little video of our Artemis 1 launch party, which was a really great time. But I can play.
Great call. The rocket is on its own. 4 great explorers ready to ride the most powerful rocket. South special waters flowing. And here we go. 10, 9, 8, 7, 5, 3.
So that was a great event, completely sold out, 320 people inside the planetarium, plus VIP on the roof. You can see we had a bunch of media crews down there at the bottom. So it's a really great time to come and talk about science in the second largest planetarium. In conclusion, understanding stellar activity and its effects on young planets requires looking at observations over lots of different timescales and in lots of different wavelengths. And by doing so, we found that young stars might actually be fairly stable over sort of years-long timescales, although we know they vary a lot on shorter and decrease steadily over longer. Thank you.
Thank you. Very good. Questions? So you didn't say, but what's the largest planetarium?
It's Liberty in New Jersey.
Oh, okay.
They beat us by 3 feet.
Okay. All right.
You mentioned both magnetic and accretion luminosities.
Mhm.
Which one dominates for AE and SU or AG?
For most of the time scale, it's magnetic activity that is dominating for both of those, although AB Auriga is much less active, although it's not accreting at all. So it doesn't have any really accretion on AB Auriga.
Are the planets known for ABSU? What are they called?
No, there are no planets known around those two. This is the table that I used to make that plot for every young planet that we know of that's less than 100 million years old and has X-ray. So the youngest one that we have is about 17 million years old. We don't have anything nearly as young as SU and AB Auriga.
I was curious, this might be well known to people who look at exoplanets. So this plot where you're showing these young but small planets.
Mhm.
Surprisingly small planets. So is not the star planet distance a factor in I'm thinking about transients. So not all flares are associated with CMEs, but young stars are much more powerful and energetic as CMEs than what we see now at the sun. So is it the distance and the higher activity a factor for that?
Yeah, so it should be a factor, right? The closer it is to the star, the more it's going to get hit with that radiation. The plot that I was showing with here, so the bottom axis there is actually the flux irradiant on the planet specifically. So that takes into account the distance between the star and the planet. So even taking into account that those closer planets are going to get hit with a lot more, a lot of these young planets that we find are really close to their stars. So they get hit with a lot more and are still larger than HD 109, 833b, and c.
But it's steady flux, right? So
yeah, this is the steady flux.
Transient doesn't take into account transients.
No. And
so
there
huge CME might be enough to completely not stir up, but completely dissolve the atmosphere of a nearby planet, maybe, you know?
Yeah, maybe. I think some of the most recent papers I've seen on the modeling of the effects of really large flares suggest that it probably can't remove much of the atmosphere. It's probably not sustained enough to get to cause atmospheric mass loss, but it does turn it into ozone. It changes the composition, but doesn't necessarily strip it away. But I mean, some of these are very small stars, so they have very big flares, and I don't think there's been enough research into how those very big flares might affect.
Any more questions online? Can you hear me? No. Okay. I just want to remind that Mackenna is here for the day today, or she's a mentee. So if you want to chat, don't miss the opportunity. And so with that, let's thank both our speakers today. And see you next week. Thank you.
Thank you.